Okay, chemistry time. Chemistry 2 time. Oh, this is the joke. I haven't done one of these in a long time, but I don't normally write what time it is, but I'm going to show you this because you're going to think this is cute with your little chemistry brain. Chemistry 2 time. You get it? It's kind of like when we name transition. Anyway, I just remember that however much you hate yourself, I hate myself more. That's not what I meant to say. However much you hate me, I hate myself more. That's what it was. The first thing is true too, sadly. Yes, that's correct. So chemistry 2 time, because this is the second chemistry class, but it's like transition metal, but whatever. Today we are talking about the gas laws. The gas laws, and because that should be review from physical science. Also gas stoichiometry. Oh no, the handwriting. Let me put everything I was holding on the ground, which was the spring from inside of a pen and the cap from my marker. Gas laws, spelled right and with appropriate penmanship, not perfect, don't at me, and gas stoichiometry. There we go, and a little flourish. The gas laws should remember from physical science. As a combination, the combined gas law is P1 V1 over T1 equals P2 V2 over T2. That's probably the most convenient one for you to memorize, where, and this is true for all of them, P is what? P is what? Density? In case the viewer, yeah, no, that's rho. Good. At first I was like, bad guess, but actually that is a good guess. But you're wrong. P is what could the quantities of a gas depend on that might start with the letter P? Pressure. There you go. Pressure. And there are multiple different ways that we measure pressure in the SI, but the most the least useful, but the most usual is pascals or kilopascals. Because as when we calculate pressure, which by the way, pressure is force divided by area. Force measured in newtons divided by area measured in square meters is a pascal. So a pascal is equal to a newton per square meter. And a newton is a pretty small amount of force. It's about the weight of a paperclip, depending on the size of the paperclip. And a square meter, well, this is a meter, right? And so a square meter would be an area bound by, this is its width, this is its length. So that force of a paperclip, the weight of a paperclip spread over that area is actually a very, very, very small quantity. And so and that's defined as a pascal. And so we normally measure it in kilopascals, but much more usually you will see it measured in atmosphere, ATM. And then rarely, but not never, you'll see it measured in millimeters of mercury. In the English system, which I won't even bother writing down, but just as a matter, in case you're interested, what is the normal way we measure pressure in the English system? Almost. Go further. Pounds per square inch. And you see how it's related. It's a force unit divided by an area unit. Pounds per square inch, kind of like newtons per square meter. So in the SI, we call that a pascal. In the English system, we call what you said pounds per square inch, PSI, pound square inch, which gives you a little insight into the chaotic, not only naming, but also abbreviation scheme of the English system. And also in the English system, we sometimes use bar, and we sometimes use inches of mercury. But these are the ones that you will find in these problems. So P is pressure, measured in those things. V is what? Volume. Good. What's the most common way that we measure volume in the SI? I shouldn't ask them that question. What's a way that we measure volume in the SI? Because we could come up with a couple, and whether one's more common than the other doesn't really matter. Not in the SI, no, but gallons we do use in the English system. What's SI? Like the metric system, the international system. There's a lot of different levels of review here, because that's something we talk about in Chemistry 1, 2. Not Chemistry 2, 1, but Chemistry 1, 2. How do we measure volume in the SI, do you think? Not the way that we measure it, but we could do that if we have the density. That would be the method of getting volume. But what unit do we use to measure volume? Milliliters. Yeah, that's one. Let's say some other ones, because that one comes up actually quite a lot, because this is commonly these are very small quantities of gases. No, not usually, because that would be the English system. Milliliters, she said. What's another one though? What's his big brother? Okay, cubic centimeters, which is not what you said, but that's probably what you were getting at. Cubic centimeters, which is the same thing, by the way. These two things are equal. Yep. What else? Bigger one. Liters. There you go. That's the one. And that's the one I would say is the most common. Also, not infrequently, but also the least frequently of these cubic meters sometimes. If you have a very large quantity of gas. For instance, one of the videos I like, and since this video is going up on YouTube, you can find this on YouTube also. The University of Nottingham has a video where they pipe helium from one place to another, and they keep the helium in big tanks, and they measure the volume of those tanks in cubic meters. And so that's, if you have a large quantity of gas, like we would measure the amount of gas in this room in cubic meters. Yeah, yeah, that's right. I'll put that in. Yeah, that's right. Check the description, and you'll find links to that. You absolutely won't, because I can't be bothered. What's T then? No, lowercase t is time. Capital T is, at least we're having fun. Capital T is Terrence. Come on, I bet you can get it. What else? This was your lab, brother. What did you change in your lab?
Theories. We changed.
I'll give you a hint. Starts with a T. What was the variable of your lab? The independent variable. You changed the
time.
You didn't change the time. Time only goes one way at one rate.
Temperature. What?
Temperature.
Temperature be T.
No, it's just T. It starts with T. And what do we measure? What do we use to measure temperature in the SI? What unit? Okay, yeah. Usually degrees Celsius, but it has to be degrees Celsius. But most accurately, or no, I shouldn't say most accurately, but for this, it must be in Kelvin. And by the way, and this is on the test, the way that you convert is degrees Celsius plus 273.15 equals Kelvin. So the Kelvin temperature is just the Celsius temperature plus 273.15. Why this, do you think? Why this number? It just seems like a random smoosh of numbers. Yes, you're right. But why this specific number? To get what? What if I had this temperature in Celsius? What would 0 Kelvin be, do you think? If you had to guess. It would be negative this in Celsius. What do you think that is? That's a fundamental physical quantity. 0 Kelvin is what? 0 Kelvin is, have you heard of this, absolute zero? Have you heard of absolute zero? We have talked about it, but not since you were in chemistry, which was a while ago. 0 Kelvin is absolute zero, where particle motion, remember, in general, you should remember this from physical science and 8th grade science, in general, temperature is a measure of how quickly and how far apart particles are moving. So when 0 Kelvin is the temperature at which particle motion is at its minimum. Its literal minimum. The smallest it can possibly be. So not always stopped in the strictest sense, but when it is as low as it can possibly go, that temperature is said to be 0 Kelvin. By the way, it's asymptotic, which means that it cannot be reached. It can never be 0 Kelvin. There's always going to be a little bit of energy. But it can get very, very close in a laboratory setting. And so to find, and that temperature, absolute zero, is negative 273.15 degrees Celsius. The reason we have that set is so that there are, if the lowest temperature physically possible is 0, what kind of math can there not be when we do these problems? The opposite of that. Negative numbers. There can't be negative numbers. Right? Does that make sense? If we set 0 on this scale at the lowest it can possibly be in physical reality, you can see how there can't be negative numbers. So like, have you ever experienced it being negative 10 degrees Fahrenheit? Yeah, some of us who have worked, not me, I'm talking about probably you, Taylor, have worked outside when it's that temperature. Negative 47, Taylor has worked. And And that's great, and we're all happy that that caused you to cry. But in kelvins, there cannot be negative temperatures at all, by definition. That's why we use them. Because if you look at this math, if you start to have negative numbers in the bottom, we might end up with negative pressures, which that can't happen, or negative volumes, which really, really, really can't happen. You can have a negative volume. What would that even look like? And also, you can't even have, looking at the way this equation is set up, you can't even have a zero. What happens if temperature gets down to zero? It ruins math. You can't divide by zero. And so in this combined gas law, by the way, this combined gas law is a combination of Charles' law, does these ring a bell? Charles' law, Boyle's law, and Gay-Lussac's law. So yeah, one of those things is not like the other. Charles' law is the one that deals with pressure and volume. P1 V1 equals P2 V2, and I'm wrong. That's Boyle's law. P1 V1 equals P2 V2. I was wrong, but only by like that much, only by 1 centimeter. Charles' law is the one that does deal with temperature. V1 over T1 equals V2 over T2. And Gay-Lussac's law relates pressures and volumes. Another, by the way, looking at these equations, what do you reckon you're always going to have to do with these equations?
Math.
Yep, you got it, math. That's what I was going for. No, you always have to manipulate, because looking at all of them, they all have at least two variables on both sides, and so you always have to manipulate. You are never going to substitute before you manipulate using these equations, because you always want to isolate the thing for which you're solving. And so whichever of these you use, Charles' law, Boyle's law, Gay-Lussac's law, or very commonly, I would just memorize this one. This is the combined gas law. I would memorize this one because, as you can see, it encapsulates all of these. Now that's the review. And you will do math with those. But where this turns from physical science review to chemistry, or in this case chemistry 2, is that we have a new equation, which we call PV equals nRT, which is the ideal gas law. I'm going to make a little box down here. PV equals nRT. Can you guess what pressure is? I'm not even going to write these ones down because you probably already know. What's P?
Pressure.
What's V? And what do you think T is?
Temperature.
Temperature. There you go. N is amount. How do we measure amount in chemistry? How do you measure the amount of a substance in chemistry? Those are all amounts, but how do you measure the actual, like, how much stuff there is in a sample of something? In what unit? No, it relates to stoichiometry again. Nope, in chemistry. What do we use to measure amount? How many atoms there are? We don't say there are this many atoms because there are too many, and so we measure it in big number. Mole, there you go. So N is amount measured in moles, and R is what we call the ideal gas constant. And this not only has units, but it has an actual quantity that you should have memorized. And I only have one of them memorized, so I'm going to write down the other ones. The most common one that we use is 0.0821 liter atmosphere per mole Kelvin. Can you read that okay? 0.0821 liter times atmosphere over mole per mole times Kelvin. Yep. L dot, like times, ATM over mole dot Kelvin. Another one we have is 8.314 liter kilopascal over mole Kelvin. And the final one is 62.4 liter millimeter of mercury over mole Kelvin. And looking at these units, what is the main difference between these quantities? In all of them we have liters to measure volume. In all of them we have moles to measure amount. And in all of them we have Kelvin to measure temperature. What's the only thing that's changed?
Atoms.
No.
Your
Of what? Measurement of what? In this one we have atmospheres, in this one we have kilopascals, and this one we have millimeters of mercury.
Your volumes.
Nope, the volumes are all liters. Liter, liter, liter. But the what quantity has changed. In this one we have atmospheres, In this one we have kilopascals, and this one we have millimeters of mercury.
Pressure?
Pressure, there you go. The other thing, the other one that we didn't talk about, yeah. So depending on how your pressure is given in the problem, you use a different one of these. And so you can convert, but you have 3 different ones so that you can just use whichever one the pressure was measured in. And the reason we have that with the type of pressure and we don't have one that says milliliters or whatever is because these ones are kind of hard to convert, the pressures are, whereas if it was milliliters, you just convert that. If it was kelvins, you just convert that using this very simple thing, 273.15. And moles is the only way we measure amount, and so that doesn't need converted. So this is, and actually this equation becomes very, very, very useful as we get into certain kinds of problems where we can just, especially stoichiometry problems, where we have an amount of a substance, we don't have to go back and forth between some pressure and temperature conditions to some other pressure and temperature conditions. Speaking of pressure and temperature conditions, you need to have memorized that this STP, here's another acronym for you, standard temperature and pressure, is defined as 0 degrees Celsius and 1.00 atmospheres of pressure. So those are those normal conditions, or what we call the standard conditions. You'll recognize that 0 degrees Celsius is actually quite cold. That's the freezing point of water. And so that's not normal laboratory conditions, but 1 atmosphere of pressure really is. That's 1 atmosphere is defined as, the reason it's called that, is that that's the pressure exerted by the atmosphere of planet Earth at sea level, or it's approximately.
So how come the other day in my lab, my thermometer said 0 degrees Celsius, so that's 32 degrees Fahrenheit.
Mm-hmm. Yeah, it did. And so you can get it in the lab. I'm just saying that's not the most common way.
Yeah, but if there's ice in it, how could it be 32?
Anytime you have the same substance but in 2 different phases, the temperature will remain at the phase point. And so if you have both water and ice, it will be 32 degrees Fahrenheit until the ice melts.
Ammonium chloride?
Yeah, that should have, since there's a solute in there, and we'll talk about that in chapter 16, I think, colligative properties of solution, so just hold on to your horses for that. But really, as we dissolve something in there, that should depress the freezing point. I would guess we just didn't wait for it to dissolve long enough, but that's a whole other problem. So these, at these conditions, and only at these conditions, we have this very common, very handy conversion. 22.4 liters of any gas equals 1 mole. And so we can convert right from how much gas there is to how many particles are in that gas. And this is called Avogadro's law. There's a song about it. Equal volumes of gases at the same temp and pressure, this is the same temp and pressure, have the same number of molecules, and that's what it is. This volume of gas at this temperature and pressure have this many molecules, 6 times 10 to the 23rd. That's a different song. Avogadro's number. And I think that was one of your vocab words. And we did learn about it in chemistry because his number is 6 times 10 to the 23rd, remember? A mole is a unit, or have you heard? That's another different song written by the same guy as the other one I was singing. So we use these conditions, or we use PV equals nRT. Okay, hold on. Okay, so those guys left. I've never done this before. I'm just gonna do it by myself, I guess. This is solo mio. Those guys left. The last thing we're going to talk about is gas stoichiometry, which is where we can convert from amount of something to amount of another thing given a chemical reaction. Don't laugh at me. Doug, just get out. Just get out like you need to. I know. I don't know who I'm going to talk to. I'm just going to have to give it to the gorilla. We don't speak his name. We don't speak his name. But I'm going to put him over here so I have someone to talk to. This is so sad. You guys, make sure you catch up on this in Google Classroom. Also, but it will make Will feel like he's included because he'll realize he wasn't the only one who missed out. You do need to watch it. Okay, so this is the part about gas stoichiometry. It really is embarrassing. Gorilla. Gas stoichiometry is where we can convert, just like we do in regular stoichiometry. If we have a chemical reaction, let's say, since these are all gases, at least at the temperatures that this deals with, if we have hydrogen gas and oxygen gas, and they combine to form water, we can now use this only at STP, or this to find out how much of these in volume was created or used. And so first thing we do is balance. Let's say we had 20.0 grams of hydrogen gas, and we want to figure out how much water was produced. The first thing we do is balance it. Boop. Boop. And now we just set up our stoichiometry conversion as usual. If I said how much mass of this was produced, let's say we want to find the volume. So we have 20.0 grams of hydrogen gas. We convert from grams of hydrogen to moles of hydrogen, from moles of hydrogen to moles of oxygen. Oh, so sorry, of water. Sorry, Mr. Gorilla. How embarrassing that I would make a mistake in front of you. And then from, finally, we're running out of room, moles of water to liters of water. So for this one, just like we did in regular stoichiometry, non-gas stoichiometry, I'm going to make a little side box over here. We add up the molar mass. We end up with 2.014 grams in 1 mole. So 1 mole has 2.014 grams. This we use our balanced chemical equation. In every 2 moles of H2, we have 2 moles of H2O. And this one, if this is occurring at STP, we can just convert right from 22.4 liters of water to moles of water. We take our given and multiply by everything on the top. I'm going to use these brand new calculators. Some people get brand new calculators. 20 divided by 2.014 equals times 2, but also divided by 2, so that's the same thing. And then multiply it by 22.4. We end up with a volume of 222 liters, and that should be the correct number of significant figures, of water. So if we had 20 grams of hydrogen to start out with, we would end up with 222 liters of water. Another kind of problem that we encounter using PV equals nRT is that we can do this same thing. We can find the amount of the substance using just PV equals nRT. And so that might be helpful if we have, let's say, let me draw a bigger box this time. Let me not bamboozle myself with having it such a small box. Obviously, for this kind of one, we need to manipulate it also. But this will let us use conditions other than standard temperature and pressure to get an amount, and then using that we can use gas liquid. So the same problem, but this time let's use PV equals nRT, and let's say it's at a different set of conditions. And then we'll talk about another way we can solve that same problem in a different set of conditions using the combined gas law instead. So we start with PV equals nRT. We will use our conditions and how much water we had to find how many moles of water that is. So we want to find PV equals nRT. We want to find the amount of the water, and so we're going to divide both sides by RT. We end up with PV over RT equals N. Let's say the pressure is 1.03 atmosphere. We had our volume of 222 liters. R, if we're using atmospheres, is 0.0821 atmosphere liter over mole Kelvin. And our temperature, let's say it's at room temperature, so 293.15 Kelvin. That will give us our N. In our calculator again, we type 1.03 times 222, enter, divide by 0.0821, enter, divide by 293, enter. We get a number of moles of 9.50. With sig figs, we have 3 sig figs, so that's right. 9.51 moles of water. And then from there, we could do stoichiometry with it fairly easily. Or at least in the normal way. I don't know how easy stoichiometry is for you, but in the normal way that we do stoichiometry, we could do stoichiometry with that amount. The other way, just as a side note, is if we had these conditions, we could use the combined gas law to switch them to standard conditions and then use that, that given amount to do our stoichiometry with the 22.4 liters equals 1 mole. And so there's a couple different ways to skin these various cats, right? Or gorillas in the case of Mr. Gorilla. There's a couple of different ways to skin this gorilla. So in the same way that we could make an incision down his back and peel him, or we could cut the skin around his neck and then fling him between our legs and have all the meat come out the other end. Just like there's a couple different ways to skin this, there's a couple different ways to do all these problems, which is we could either use PV equals nRT, or we could use the STP rule, Avogadro's rule, with the combined gas law. Either way, we end up with either an amount or a volume, and then we can do stoichiometry with it. Your book also has a discussion on how we can use molar mass to define the density of a gas, or density to find molar mass. And what that amounts to is basically that just heavier gas molecules, or heavier gas atoms, whatever the gas is, heavier gas particles would also make a denser gas as well. And so if we have the two equations that you would need for that are molar mass times pressure over this ideal gas constant times temperature equals density, rho. Your book says D, of course, but you can use it to find density, rho. And that also tells us that the denser a gas is, generally the slower it'll be moving. It has lower kinetic energy at that point too. There is no one for me to ask if you have questions. The gorilla is not going to answer me. If it does, we'll have other problems. But if you have questions, I guess you can put them in a comment, or you can bring them to class with you. And this is the time I normally say bye, but there is no one to say bye to. There is no one to say bye to.